Hi, it's Ms. Murat with help on today's assignment, Unit 4, Lesson 7. So we learned a lot about half-life today. And so looking at number 1, the half-life of carbon-14 is about 5,730 years. A fossil had 6 pictograms. Here's the half-life. Here's how much the fossil had of carbon-14 at one point in time, and that tells us what a pictogram is. Which expression describes the amount of carbon-14 in pictograms T years after it was measured to be 6? Okay, so T is going to be a measurement of just 1 year. And so if the half-life is 5,730 and the original amount, or whenever it was discovered, was 6. So I know that 6 is going to be in the initial amount. I know I'm going to have to multiply by 1/2 because the decay factor in a half-life is always 1/2. That's why it's called a half-life. And if it takes 5,730 years for that to happen one time, then each year it happens just a little bit of it. So we take the number of years, whatever T is, and divide it by how long it takes to happen in one half-life, 5,730. Okay, so it looks like the equation that matches what I just wrote up there is going to be equation A. Okay, number 2. The half-life, again, same thing, so 5,730 years. A tree fossil was estimated to have about 4.2 pictograms of carbon-14 when it died. The fossil now has about 0.5. About how many years ago did the tree die? Show your reasoning. Okay, so again, I'm going to set this up, 4.2. And then I'm going to multiply by 1/2 to the T over 5,730. Okay. So as I'm thinking about this, I might kind of look at my calculator, and eventually you're going to learn some tools to solve this exactly. But right now, I don't know how to solve exactly for an exponent, but I am just going to think logically about it. So I'm going to keep track of how many times, if I multiply this by 1/2 or 0.5. So in one half-life, there's 2.1. I'm going to multiply it by 0.5 again. So that's 2 half-lives. That's 3 half-lives. I'm going to say 3 half-lives because this is really close to 0.5. And it does say about, and about. So we're going to estimate. So I came up with 3 half-lives. So 3 times 5,730 is 3 times 5,730, 17,190. And these are years ago. Okay, so 3 half-lives, each half-life is 5,730 years, and so multiply them together, and that's what we get. Okay, number 3. Nickel-63 is a radioactive substance with a half-life of about 100 years. An artifact had 9.8 milligrams of nickel-63 when it was first measured. Write an equation to represent the mass of nickel-63 in milligrams as a function of. So first is going to be time in years, okay? So time in years, and it takes 100 years for one half-life to happen. So 9.8, I'll just use F of t. The initial amount, 9.8. This is a half-life. And every year, it's going to decay just a little bit out of the 100 years it takes for an actual half-life to happen. Okay. The next one is we want to say, well, what about if we use D? And D is going to be time in days. Okay. So this is a little bit each year, but how much is that going to be each day? Well, I know there's 365 days in a year. So out of the 100 years, each day is going to be 1 day out of 100 years. So 1 day out of 100 years. Okay, now let's think about that. If there's 365 days in a year, then each day is out of, instead of 100 years, 100 times 365, so 36,500 years. Okay, and so now when I write the function f of d, everything's going to stay the same, except I'm going to use the fact that there's 365 days in each of those years in my exponent. So f of d equals the initial amount, 9.8. It's a half-life, so 1/2, and then d over 36,500. All right, moving on. Okay, Tyler says the function f of x equals 5 to the x is exponential, so it grows by equal factors over equal intervals. That is true. He says that the factor must be the 10th root of 5 for an interval of 1/10, because 10 of those intervals makes an interval of length 1. Do you agree with Tyler? Okay, so if I know I have f of x equals 5 to the x, and what he's saying here is that if you take an interval of 1 and you split it up into 10, then this tiny space right here is 1/10 of that interval, right? So I would say, oh, the factor for this tiny little interval right here, if the whole thing is a factor of 5, then this would be 5 to the 1/10. And so is that equivalent to the 10th root of 5? Oh, well, when we have a fraction exponent, the denominator of the fraction is the index of the root. The base stays the same, and then the numerator is the exponent inside there. And since 5 to the first is equal to 5, this is equal to the 10th root of 5. So do I agree with Tyler? Sure do. And everything I did to get there is the reason why. Okay, moving on to number 5. The population in a city is modeled by the equation P of D equals 100,000 plus 1.03 to the D, 1 plus 0.3, sorry, to the D, where D is the number of decades since 1910, so 70. D is the number of decades since 1970. So again, a decade is 10 years. So what do the 0.3 and 100,000 mean in the situation? So the 0.3 means that the population is increasing by 30%. So that means increasing by 30%. because 0.3 as a percent is 30%. And then the 100,000, well, that's the initial amount. And since the function represents the population in decades since 1970, that means that the 100,000 is the actual population in 1970. Okay? Next, write an equation for the function f to represent the population y years after 1970. So now we're going to go, this initial function represents decades. Now we're going to change it to years. So I could say f of y equals 100,000. Now, I'm going to go ahead and combine that to 1.03. And since a year is 1/10 of a decade, I can do the 1/10 here and then raise it to the y, because it's 1/10 every year. So that's one way I could write it, or just adjust for the fact that there's 10 years in a decade right in the exponent. Okay, so those are completely equivalent. Next is going to be for centuries. Oh, for centuries. Now this is gonna need to be a little bit bigger, because a century is 100 years. There are 10 decades in a century. And so for this one, we can adjust the exponent inside or outside the parentheses again. It's going to look a little bit different because now we're looking at a larger period of time. So I can say 1.03 to the 10th to the C for centuries. Oh, and actually it says to use. My notation is wrong. It says to use G, and then, so it's function G and it's G of C. C for century, sorry about that. Or we could put these together in one exponent. Oh my goodness, I'm just so accustomed to using F, but G of C, the 1.03, and now to the 10C, since there's 10 decades in a century. Okay, so either way. Oh, we're almost done. Number 6, the function f is exponential. Its graph contains points 0.5 and 1.510. Find f of 3. I'm going to use a table to find f of 3 because, so I have like x and f of x. So I know when x is 0, f of x is 5. When x is 1.5, x is 10. And then since this is exponential, I need to ask myself, what do you multiply 5 by to get 10? You multiply it by 2. And so very conveniently, f of 3 is going to be like, we're counting by equal intervals. It's plus 1.5 and plus another 1.5. So if these intervals are equal, which they are, then I just multiply 10 by 2 and I get 20. So f of 3 is equal to 20. So if I'm going to use the value of f of 3 to find f of 1, how could I do that? How could I use the value of f of 3 to find f of 1? Okay. So if I'm thinking about this, going from I'm going to kind of draw a little graph because that's going to make it easier for me to explain. 0, 1, 2, 3. I know this. I know 0 is 5. And I know at 3, it's at 20. Okay. So it's something like this. And I need to figure out this at 1. Okay. So I know to get from 5 to 20 is multiplying by 4, right? And then this is 1/3 of the way, the distance between 0 and 3. 1 is 1/3 of the distance between 0 and 3. I'm going to use that as an exponent, 1/3. Okay? So I know that, again, to get from the 0 point to the 3, I'm really multiplying by 4, right? So to get just one space, I'm going to use 4 to the 1/3. Okay, that's going to be the growth rate for a distance of 1, 4 to the 1/3. If it's a growth rate of 4, to go an interval of 3, then to go an interval of 1, it's 1/3 of the way, so 4 to the 1/3. So since the value at 0 is 5, the value at 1 is going to be 5 times 4 to the 1/3. And 5 times 4 to the 1/3 is equal to about 7.9. Okay, about 7.9. Okay, and then what is an equation that defines f? So in order to write this equation, we need to know the initial amount, which is 0. We already found that. I'm sorry, the 0 is 5, so the initial amount is 5. We need to know the growth rate when the interval is 1, which we found with 4 to the 1/3. And so I can write 4 to the 1/3 and then to the x, or I could approximate that. But because it's going to be like a long decimal, I'm just going to keep it as 4 to the 1/3. Okay. All right. And then finally, number 7, select all expressions that are equal to 8 to the 2/3. So 8 to the 2/3, I can rewrite that as a root. It's the cubed root of 8 to the 2nd. That looks like option A. We can rewrite this. The power of 2 doesn't have to be under the radical. It's equivalent. Remember that if it's outside the radical. That's the same as B. This one is not equivalent. The next one is 2 to the 2nd. I'm going to hold off on that one for just a minute until I think what we could do is actually just evaluate 8 to the 2/3. And this is why I really like knowing the back and forth relationship between roots and fraction exponents, because it's so easy to type into my calculator 8 to the 2/3. 8 to the 2/3 is equal to 4. And so I know that 2 squared is equal to 4. 2 to the 3rd is equal to 8, and then obviously 4. So A, B, D, and F. All right, that is the end of your assignment. I hope you found the video helpful.